Suppose that I have a little glass bowl with some positive charges. Let's say 0.001 coulomb of positive charges, and suppose that I have a smaller ball. I have a smaller ball with some negative charges. Let's say 0.0001 coulomb of negative charge, and this is at a distance of, let's say 2 meters. Let's say this is at 2 meters away. Now we know that we can use Coulomb's law to calculate the force. On this negative charge due to the positive charge. Okay, let's say the force is F. Now, if I use Coulomb's law, this is what I get. It goes something like F is equal to 1 over 4 pi epsilon naught, and then right, I need the charge. Let me call this charge big Q, and I call this charge little q. So there'll be big Q times little q divided by, let me call this distance r, divided by r squared. So if I put all these numbers into the formula, and we know what epsilon naught is, just write it down at the bottom. Epsilon naught is equal to 8.85 times 10 to the power of minus 12 farad per meter. I think it's per meter. So if I put all these numbers in here, and using my calculator, I would find 224 newtons. So that would be the force acting on this. Now what I like to do is to compare this equation with what I have, with what the equation that I have for gravitational force. Let's say I have let's say this is the planet Earth. This is the planet Earth, and I have a ball which is some distance away. So that's a ball. Now the gravitational force on the ball I can also calculate, but this time using another formula, using Newton's law of gravitation. So let's say the ball is at a distance of r away from the center of the Earth. Let's say the mass of the Earth is big M, mass of the ball is small m. So according to Newton's law of gravitation, I have F is equal to G gravitational constant. Big mass times small mass divided by r squared. And when I put all the numbers in, I would find an answer. Now I'd like to compare these two formulas and look for what is similar. Now the two formulas actually look quite different. I mean, we have GMM, we have 4 pi epsilon naught QQ. The only thing that looks the same is the R here and the R here. Okay. Now, but I would like to highlight this similarity, this R, which appears in both equations. And there's something important about this similarity, even though it just looks like there's only one thing that is similar, just the R, and that all the rest are different. Now what is important about this is that of all the symbols here, R is the only one that can change with the position of the object, whether it is the ball or the charge. Now the other terms are constant. They don't change. And the charge and the mass don't change when you move the object around. Okay, so of course we can always change the charge, add more charge, or just change the ball to a stone or something else with a different mass. But for now, I'm just going to consider the situation where we keep the same objects and we would just move the R around and see what the forces are and maybe what the energies are. So for such exercise, right, for such exercises, it is mainly the R that is important, and I can think of the rest of it, in this case the GMM, and in this case this part here, right, 1 over 4 pi epsilon naught and the QQ there, as just a constant, right, as just a constant. So what I could do is I can think that both equations, both the Coulomb's law and Newton's law of gravitation, I can think that they both have this form, have the form where the force is equal to some constant divided by r squared. Right, some constant divided by r squared. Like the constant here, here is the GMM, that's my constant. Coulomb's law, this is my constant, the charge and the permittivity. And the r squared is the only thing that varies. Now this understanding is useful, particularly when we want to think about the potential energy. Now let me recall the gravitational potential energy. It has this formula. Right, I shall call it EP then. EP for gravitational potential energy. Just write this down just to clarify. So I'm talking here about potential energy. Okay, so if you recall from my earlier videos on gravitational potential energy, this formula is minus GMM over R. Okay, very similar to the formula for force, except that instead of r squared, I have r down here, and I have a minus sign. So in my earlier videos on gravitational constant, I've explained what this means, how you can derive it, by considering the work done against this gravitational force, and either using area under a graph of the force or using integration. So please refer back to that video to refresh the ideas. Okay. So with this potential energy, let me also remind ourselves of what this potential energy mean. What does this mean? It is actually the work done to bring a body from infinity okay. Now let's be more precise about this. So if I say, when we say potential energy of a body like the ball, we have to refer to a particular position. So in this case, maybe a distance r from Earth or from some other mass. So the potential energy at a point, right, right, is the work done to bring a body from infinity to that point. Okay, so that makes it a bit more specific. So work done to bring the body from infinity to that point. And you also recall from my earlier videos on gravitational potential that infinity can just mean you can just think of it as some place very far away where the gravitational force is effectively zero, and bring it all the way here. And also that the purpose of defining a potential energy, or even if it looks strange to define in terms of infinity, the purpose is that it will be useful. It would be mainly useful for us to find changes in potential energy when the ball moves from one point to another point. Right? We are usually less interested in the actual value of the work done from infinity, but we are more interested in what happens, how this potential energy will change. Because say a decrease in the potential energy when you drop the ball will be converted into kinetic energy. Now, so what I'm going to do is to see how we can use these ideas in electric fields as well. So in order to do that, we need a corresponding formula. Okay, a corresponding formula for the potential energy of a charge. So if this is the formula for gravitational potential energy, what is the formula for electric potential energy? Now we can actually go back to the earlier videos on gravitational potential energy and repeat the same steps starting from Coulomb's law instead of Newton's law of gravitation. And you'll find that you can use the same steps because the steps mainly involve calculating with r, keeping the rest of the formula constant. Okay, and since we also have r squared here, like for Newton's law, we can go through the same steps. quite easily. Now, but since we already know the answer, that the answer is a constant divided by r, I can think of this formula. As potential energy is equal to minus of a constant divided by r squared, divided by r, right, where the constant is the g and n. So the gravitational potential energy has this form, right, constant over r, which is minus sign. So the same way, we would expect that if I start with the Coulomb's law, alright, because it has the same r squared as the gravitational law, I would end up with a potential energy formula of the same form. It will be something over r, and there will be a minus sign as well. Okay. The difference would be in the constant. In this case, the constant is this knot here. So let me write this out. So it will be QQ on top over 4 pi epsilon naught times r. 4 pi epsilon naught. Okay, so with our understanding of the similarities between the electric force formula, the Coulomb's law formula, and Newton's law of gravitation, we can write down the formula for the electric potential energy quite easily just by comparing it with the formula for gravitational potential energy without having to actually go through all the same steps again. Alright, but in doing so, it is important that we have a good knowledge of how this was done for gravitational potential energy. Okay, so now that we have a formula for the electric potential energy, we can actually use this in the same way as we did for gravitation. For example, if I imagine starting from this point, if I release the charge, if I let go of the charge will start falling, will get attracted by the force and start falling towards the positive charge. We could actually use this to calculate the change in potential energy and therefore the kinetic energy of the object as it falls.